start the recording, and we have that. And Annie said the sound check was good. And we're going to, let me do this first. I'm going to begin by polling the students who are with us this morning, just checking to see, do you have questions or concerns, and or comments or whatever, just checking in with you. This can be very quick. If you say, no, I'm good, then, I know you're good and I will move on. But otherwise, I will, I will try to address any concerns that you might bring up. And in fact, I'm glad I'm doing this. I'm glad I have the luxury of doing this. But one of the things is I was disappointed in something I found this morning, and so I want to raise it with you right now, and then I won't talk about it later in the course. But there was a student in my discrete math course who dropped the course. And that's pretty early to drop the course, but I know, things happen and things like that. Like sometimes people have to move, or, there's all kinds of things that really happen. But under the reason for dropping the course, the student said online versus classroom. Well, I know this is online right now, and I can't predict the future, but my plan and my hope is that this is not an online course. So if I had had an opportunity to talk to that student, and actually I did, I went through with my discrete math students and I asked them questions too. But this discrete math student didn't bring that up in the comments, but then he dropped the course and he said online versus classroom was his reason. Well, I hope that the discrete math course, as well as this course, ends up being a classroom course. So anyway, I just want to say that, and I really do want to hear what you have to say. I'm investing class time, doing this, so I think it's good. And Annie, I know you just volunteered, but your name is first alphabetically order here, so I'm just going to poll you and ask, do you have any questions or concerns or things you want to share with us at this time?
No, not really.
Okay, excellent. That's fine. And I'll just take that. That's good. But also, if you have something you want to bring up, that also is good. Okay, so thank you, Annie. And by the
Um,
way, doing a good job. Yeah, Cecilia, you're not next.
okay.
Artemio Serna is next. And by the way, Cecilia, you follow him. So I will be calling on you, so I won't lose anything that you're, willing to share with us and things like that. But next, and I'm just going through polling people alphabetically order to make sure I don't miss them. Okay. And again, Cecilia will get a chance, and everybody will get a chance. Artemio Serna, how are you?
I'm fine. I'm fine.
Okay, no questions then.
No, no, no.
All right, excellent. That is wonderful. And now, Cecilia, it is yours, but now in my head, I can put a check by Artemio and said, "Hey, I did check in with him." So, Cecilia, how are you doing today, and what was on your mind?
I have a question. I know you've discussed the LSAs and their due dates, but remind me where we do them. Like, is there something online where we can do them, or do we have to do it on paper? And if we have to
You
do it on paper, how do we turn it in online?
okay? Excellent, excellent questions that we should that should be uh, done. And let's see, Hare Patel has raised, I think it is her hand, but I'm going to not call on her right now. I'm going to answer this question, and then I'm going to call on her because she was commenting maybe on maybe on that thing. Um, okay, here is what will happen. It is not an online, well, it's kind of online, but here's what you should do. You should write your solution to the LSAs on paper. And then you should turn the LSAs that you wrote your solution on paper into PDFs. And I have ways to do that and to show you if anybody, struggles with that. I can help you, and so can Linda Shaw. But beyond that, there is going to be a place that is going to be called PDF upload, where you can upload the work. Now, also, Cecilia, I'm going to say that I'm hoping that this is a short-term issue, just for maybe the first LSA, because what I really hope will happen is that we're back in a classroom. Now, I can't predict the future. I don't know. But you know, we're dealing with this. So anyway, to you know, kind of underscore what I was trying to say then is, for LSA 1, you will turn it on online, and there will be a place that is called PDF upload, where you either take a picture and turn it into a PDF and upload that, and that will be what you will do. So Cecilia, did that answer your question? I hope.
It answered that question, but I'm also now wondering, you probably already answered this, but is there someplace on Blackboard that we can look at the problem?
Yes, when in fact there's two places on Blackboard. Now, or let me say it a different way, Cecilia, a more accurate way probably. There will be two places on Blackboard where you can do that. One is I introduced it during a video. So as you watch that video, as an active learner, you pause those videos and things like that. So that is one place that LSA 1 is on. Now, I don't insist that students, actually, I encourage students to actually take notes and pay attention during the videos, but I will be posting LSA 1 separately in your syllabus tab. I might not have done that yet, probably not. I was juggling a bunch of things, and but that's not due till February the 7th. And so, you know, that will be, you know, there will be plenty of time to do that. So then, Cecilia, to answer that question, it is in Blackboard, and it will have two appearances there, and you'll know about it because when I post it in the syllabus tab, and my guess is I haven't done that yet, what I will do is I will you know, send you an announcement and an email saying, hey, it's there now. But that, so anyway, so that was your second question, I think.
It was, and you've answered it. Thank you.
All right, excellent. And your questions are always welcome. Now, Hare Patel, you were, whoops, I'm looking, oh, there, okay. You're actually next, and I know you raised your hand too. And normally I would, you know, I would call on you, but and maybe you were trying to help me answer Cecilia's question. But anyway, you were next, so I'm polling you. I see you've gone on mic. That's good. So how are you today, and what do you have to contribute?
I'm good. I was just gonna give her a solution, what I did.
Oh, okay. Well,
Yeah.
I'll tell you what, why don't you share that, not only with Cecilia, but with the whole class, because some other people might be doing it. And by the way, I have my own pet ways of doing that, but you guys might have better ways. So go ahead, Hare, please.
Yeah, so I just have the OneDrive app in my phone. So and then just sign in with my school account, and there's a plus button. You just take a picture. There is like a picture option, and you just take a picture of whatever you want to take picture of, and then you save it, and then you just go on Blackboard and the assignment, and then you just do the Blackboard iCloud folder or something. That's what it's called, I think. And then you will be able to pick out that picture.
Could I comment on this?
Sure, I guess so.
So that sounds like a good solution, and if you want to do that solution, you absolutely could. But I'm not doing it just because I don't really like taking pictures of my paper. It usually doesn't look good.
Okay. Well, so I'm going now. I'm going to, you know, kind of pile on here, and I'm going to talk about my solution. But my solution also involves taking a picture. And again, I'm not insisting how you do it, and you can find a way. And if and there's all kinds of ways to deal with this. And again, I hope this is a short-term issue for our class. But there is an app, a free app on your phone called, let's see, I'm going to say it's called something like, uh, well, it's called Office something. Anyway, it's a free app, and I can share that with you. But then you use your cell phone to take a picture. Now, I realize, Cecilia, that's still taking a picture, okay? And there's but you don't have to do that. There's all kinds of PC, not PC, but there's all kinds of power ways. For example, when I'm making some of the slides for my class, I end up scanning using a scanner and emailing it to myself, and it gets emailed as a PDF. So I don't want to spend the whole time, debating the technical merits of this, because it's more than a week before this thing is due. But yeah, just try to find a way. And so thank you for your ideas and comments. And Harry, you didn't have anything else?
No, that was all.
Okay, and Cecilia, you went on mic, so you have something else?
Sorry. Okay, so I was thinking, would it be okay if I tried to post my solution to the problem through Google Docs or Google Slides? Try to.
No, because I'm not going, well, okay, you can do whatever you want, okay? And so let me just say that. But there are, I don't know, I'm going to say a dozen, something like that. Actually 14. There are 14 students who are in attendance here, and some people will say, oh, I want to do it in Discord, and somebody else says, I want to do it somewhere else, and things like that. So you do what you all want, and let me know, and I'll do it. But I really would like for people to maybe strive to do it the way I'm suggesting, because you might learn something and develop some additional capabilities, okay? And I have put capabilities in there. I have a PD upload space for you and things like that. I'm not going to be unreasonable, but also I'm like you all, I'm pretty busy. And so for me, checking 14 different sites and protocols for people turning things in is going to be challenging. So anyway, the answer is yes, Cecilia, you can do whatever you want. Let me know exactly what you want and give me detailed instructions for how to access whatever it is, and I'm sure we'll be fine. But I'm also going to encourage people to maybe see if they can expand their horizons and and do things in a uniform way. So Cecilia, the answer is yes, do it however you want. Send me emails with detailed instructions about what you're going to do,
Okay.
and I will do it. Okay, thank you.
Yeah. Okay. I just want to say say that if I used Google Docs or Google Slides, that shouldn't be too difficult for you, right?
No, actually, I'm very good technically. The difficulty is having 14 different students doing 14 different things, just because they want to do it their way instead of
Yeah.
the
I'll
way
try
I'm
to.
trying to do it. Okay, and now people are telling you there's some things there, there's multiple applications, and there's many ways you can do this. And you can also interact with Linda Shaw or me during my office hours, and we will walk you through how to do what we're asking you to do. But if you want to do it a different way, certainly I'll let you do it your way, and I will ask you in turn, though, to explain in
Yeah.
detail how to do it, where you're putting it, and things like that, because again, everyone is busy. So thank you all for all your suggestions there, and Cecilia can read those comments
Yeah.
as well
Okay.
as me.
And yeah, I
And
do.
Herr Patel, do you have anything else to say, or are you good?
No, that's it. Thank you.
All right, excellent. Jeffrey.
I don't have any questions.
Okay, that's good, and it's always good if people have questions. That's good. Joseph Vaselli, I think.
Yeah, I'm all good.
All right, excellent. Kang Lee, how are you?
I'm good.
Okay, no questions then, I'm assuming. Mark Zayden. I can't hear you yet, Mark.
He's
Okay, I
probably
don't know.
chatting about or something.
No, you see, I hear a bong when people chat. Okay, and maybe he chatted, but I was counting the chats. And his mic is not working. Now he did chat. His mic's not working. Mark, are you okay? Yes, good. Okay, so we will move on now. Michael Showman. And Michael, just chat at me if you or if you're having technical difficulties, or speak if you can do that.
No, yeah, I'm good.
All right, excellent. Thank you so much. I'm moving on to Steve Terco.
Yeah, I'm all good.
All right, excellent. Timur, how are you?
I'm good.
Excellent.
I'm
And the
good.
last person, oh, I'm sorry, Timur, did you have something else?
No, I'm fine.
All right, excellent. And let's go to Tony Beliza. So Tony, how are you? No questions. Okay, so that is good. And your questions are always welcome. But I like to do this, especially since we're doing something and we're spending and it's okay to spend time on all these submission protocols and stuff like that. But I hope that is a short-term issue for this class. Okay, so let's dive in and do some work then. And so
Hey, Professor,
let's
just
see.
really quick. I didn't hear my
Yes, go
name
ahead.
called. I just wanted to
Wow,
let
I'm
you know.
sorry.
Oh, no worries.
Let me think about it. Oh, Alex, you know, um, I started this list alphabetically, and I started it with Annie. And again, I'm not worrying about if you were here at the drop, at the starting event or not. But Alex is alphabetically precedes Annie, and I started with Annie and went through. So that's how come I didn't sort of realize that you were there. So thank you for being here. Do you have anything on your mind?
Oh, no, I'm good. I just wanted to make sure that, like, in case this was for attendance or something, that you knew I
Yeah,
was there.
this is not for attendance because I'm way too busy just to take attendance.
Oh,
Taking attendance is a kind of a high school thing, and I work hard to make this not be a high school course. Okay, so that's good. Now let me go back to Annie. I am going to be asking you in a moment if you can see. In fact, Annie, I guess I'm going to ask you this way: if um, I'm talking about something and you can't see it, just jump in and tell me, okay? So I'm going to share my application screen. Haven't shared it yet. But now, Annie, you should be seeing a PowerPoint slide.
Yeah.
All right, excellent. And maybe I'll just trust you, so I'm not always saying, hey, are you seeing what I mean? Maybe I'll do that. I already told you the story about the person that dropped because he said, oh, the course is online. The course isn't online yet, anyway. And in fact, I hope it's not. Okay, I am going to make a little bit of announcement here. Linda Shaw, and I've told you that she's a wonderful resource. I've worked with her many times and things like that. Linda also, in her spare time, coaches a high school math team who goes to competitions, and they just won the regional event, the team that she coaches. And so I'm just making a mention of that wow, she's a good coach, she is a good tutor, and going to the GSGs would be good. Now I did polling, so that is good. Polling meant I talked to each student about things in case they had things going on. Your questions are always welcome, but I'm not going to pause for just a polling question later. Now, I have been posting videos because right now this course is semi-online. And I do expect you to watch these videos because I'm covering content in these videos. Now, some of you, and again, Alex probably probably knows. In fact, well, actually, I know. I posted something at I'm going to say 3:30 a.m. this morning. Don't quote me on the time, but there's a video there, and some of you students didn't get up to watch that video yet, and that's okay. But it is there for you to watch. I'm assuming you are going to watch it. We're going to have a weekend of downtime where we're not, having lectures like this and things like that. And so, even if you're behind on the videos, you can catch up. So that is, an expectation, and you should be doing it. But there are some highlights from that video that I posted at 3:30 that we're actually going to be using. Now, I'm going to make mention of these things, but there is in-depth discussion of all of these topics in the video that I did. So for example, there are things that are called properties of limits that we are going to be talking about. Um, and I'm going to make reference to them, and I say, well, as we learned in the video, and then I'm going to talk about what it is and things like that, but I'm going to be using that. I'm also going to be talking about the concept that was introduced in the video, and again, I'm going to not introduce it in a full, not completely replicating the lecture that I've already posted on YouTube, but I am going to talk about continuity, and we're going to use continuity to solve some of these problems. There's a technique that I call counseling a common factor, and the notes may call it something slightly different, but that's a technique that we introduced. And also there was another technique that was introduced called creating a common factor. Now what we're going to be doing is we're going to be going through and we're going to be doing problems that use these capabilities. And so I'm going to be solving problems. You have opportunities to ask questions and things like that, but I'm building upon the videos with several examples. And then I am prepared. I don't know how, I never know exactly how the class is going to go, but I am going to tell you that we're in very good shape. I'm going to introduce yet another result or theorem called the Squeeze Theorem. And I'm prepared anyway, to apply the Squeeze Theorem to our discussions today. So it's a good day. Okay, so let's go to then this next problem, and this is a limit that you need to evaluate. And if we were in a classroom and I could see you guys and things like that, I'd probably ask someone to read this, because it is important that you can speak math as well as read math. But since we're not in a classroom and we spent a lot of time having some individual dialogue, which is fine. I'm going to read this, but I do expect you to be able to read this. So the way I would read this is, I'm asking you to evaluate the limit as x tends to 3 of the square root of x some of these people are being relentless, so I am turning off my phone. Okay, so the phone is now turned off. Okay, so this problem would be evaluate the limit as x tends to 3 of the square root of, I heard some kind of a comment button, so I have to stop sharing to go to see what may have happened on the comment button, if someone did make a comment. And let me see. Okay, someone said, what was that music? Well, I was trying to explain that. I thought people realized that that was my phone, and my phone was going off, and the person was being relentless, calling me. I don't owe them money, but they want me to arrange to pay them money, and I'm getting some quotes on some work. So that was my phone, and that's what I was saying whenever I was talking to you, and I said I'm turning the phone off so that we don't hear from them again. So that was the phone. Okay, so now we've answered that question. And now, Annie, I have to go back and share content again. So I'm going back to my application screen. It is here, and eventually we'll see. Okay, so Annie, you can see and Annie, I'm sorry, but I have to do this when I jump back and forth because I don't want to leave people alone. You can now see the PowerPoint slide, yes?
Yes.
Excellent. Okay, so the way you would read this is limit as x tends to 3 of the square root of x plus 8. Now it turns out that the graph of this is a continuous function. And in fact, wow, I guess I have to do this too. So I've stopped sharing and I'm going to go to the whiteboard and I'm going to share there. So Annie, now you can see a whiteboard.
Yes.
Okay, I know this is tedious, but it's tedious for us all. Okay, so I have the limit as x tends to 3 of the square root of x plus 8. Now, the graph of x plus 8, and it's useful to think about that, is shifted 8 units to the left, and it looks like this. But 3 is over here. So you see, we can, and this is the way in the video and whenever I teach class, I talk about continuous functions. And a function is continuous at a point in its domain if you can trace it without lifting your pencil or your cursor or whatever. So you see, I can trace this within its domain and never lift my my cursor. And that means that this is what's called a continuous function. And again, I talk in great detail in the videos about continuous functions. But one of the punchlines and one of the big takeaways is if I'm dealing with a continuous function, the way to evaluate the limit as x tends to 3 is just see, can I plug 3 in and get an answer? And in this case, I can, because if I take x to be equal to 3 and plug it into the function, I get the square root of 3 plus 8. Now 3 plus 8 is known to be 11, so the exact answer to this problem and the only acceptable answer in this class to this problem is going to be, the answer to this is equal to the square root of 11. Now, what that means is, and this is what I say in the video, and I'll probably say it so often, people would be tired of hearing it, but the first thing you think about whenever I ask you a limit question is, can I just plug the value in? Now, the answer to that often will be no, but if you can, then you can plug it in, and the good solution is just plug it in. So I tell students, whenever I ask you a limit question, you should think maybe only for a nanosecond, which is 10 to the minus 9 seconds, but maybe only for a nanosecond, but you say, oh, can I just plug it in? And in this problem, the answer is yes, I can just plug it in. And the reason I can do that is because this is continuous. So the answer to this problem is square root of 11. Okay, I'm going to pause for a count of 5 just to see if anybody have any questions about what I said. And if you have technical difficulties, certainly comments are fine, and I'll jump back and forth across all these different applications and things like that. But also, I'm very happy if you have a question, and if your technology allows for you to go on mic and ask the question. And again, hopefully one day soon we won't be doing this this kind of thing. So I'm counting to 5 Mississippi to give people an opportunity to ask a question if they have it. Okay, I didn't hear anything, so I'm going to say that that's good. And I'm going to share my application screen with you, and we're going to go back. So we did a problem, so that was good. And I'm going back to the talking points. Okay, so the answer to this problem was the square root of 11. Here's another problem though. And this one, the question says the limit as x tends to 3 of tangent, and this is pi over 4 times x. Now, by the way, one of the things that's important for you guys to realize is, and mathematicians sometimes don't write all the parentheses that they could, perhaps, right? So this is the tangent of, so there's like after this tangent, there's really an implied parentheses, and the argument of the tangent function is pi x over 4. Now, okay, so this is the question, and the first thing that a student should think about is, well, is this a continuous function? Or actually, the student doesn't even have to do that. They may remember that, oh, Jim said in a problem like this, what I should do is I should see if I could just plug 3 in, and the answer is yes, you can. Just plug 3 in and get an answer. So this is the tangent of 3 pi over 4. Now the tangent of 3 pi over 4, you have to be able to answer that, and you have to be able to answer that without a calculator in this class. And I've talked some about that in some of the videos and things like that. But you say, okay, so I think about, can I just plug it in? And the answer is yes, I can plug it in. And so what happens is the answer is going to be the tangent of 3 pi over 4. But then to get full credit on the problem, you have to know what is the tangent of 3 pi over 4. And the answer to that is going to be -1. Okay, so I'm going to pause for a count of 5 Mississippi in case people have questions about this problem. And if not, we'll move on to yet another problem. Okay, I hit 5 Mississippi. Now your questions are always welcome, but apparently there were no questions, so that is good. Now let's look at some other things. Okay, now this is a problem, and I think what I'm going to do is make a few notes. But this is a problem that involves the properties of limits that I talked about in the video. And again, I'm going to use them to solve this problem, but I encourage you to watch the video so you understand that. Okay, so the limit as f of x, the limit of f of x as x tends to c is 2. And the limit as x tends to c of g of x is 3 over 4. Now that's the given in the problem. But now what you're supposed to do is you're supposed to find the limit of 4f, the limit of f plus g, limit of f times g, and the limit of f over g. Okay, now I'm going to a whiteboard and we're going to solve all of these problems. And I am going to underscore that these are properties of limits that you should know, and these are properties that were introduced in the video, but I'm covering them now also, but within the context of a problem. So I'm stopping sharing that, and I am going to go to sharing my whiteboard again. And I can use the magic button to erase all the whiteboard. So I'm going to do this. All right, so, and I am going to be talking a bit as I go through. So I want to know the limit as x tends to c of 4 times f of x. So you see the function that I'm taking the limit of is 4 times f of x. And people won't always write that parentheses, but I did write that parentheses. Now, the property that we learned, and I'm being a little bit irreverent with the property now, but if I have a constant, in this case 4, times a function, if I take the limit as x tends to c of a constant 4 times f of x, I can jerk that constant through the limit sign. This is one of the properties that I did in the video, and a property that you want to use. Now, I said you can do this. I would encourage you to do this, and as a practicing mathematician, I do this 10 times out of 10. I will jerk that limit through, I will jerk the constant through the limit sign. So this is the same thing. This was the theorem that I proved in the video, is I can pull the 4 outside. I proved it actually using the epsilon delta technique. So I can pull the 4 out, and this is 4 times the limit of f of x. But now the order of operations then is the 4 is just out there, but the problem told me that the limit as x tends to c of f of x was 2, so this is 4 times 2, and that's going to be 8. Okay, I'm going to pause here in case there's a question, and I'm going to count to a beat of 5, I guess. Okay, excellent. Now I'm going to just erase this. I'm going to talk about the next one. Now the next one that was on that list of problems that I showed you we were going to do is this. Calculate the limit as x tends to c. But I'm taking the limit of, this is f of x plus g of x. Now, the thing that I cover in the video is that the limit of the sum is the sum of the limits. And in fact, I give you an epsilon delta proof of that as well. So what we learned, and I'm going to say this in my own slang, the limit of the sum is the sum of the limits. So I am applying that property that I talked about, and you are free to apply it as well. So the limit of the sum of two functions is the sum of the limits. So this is equal to the limit as x goes to c of f of x plus the limit x tends to c of g of x. But in the given of the problem, I told you that this first part was 2, and the second part is 3 over 4. And so the answer to this problem is 11 over 4. And by the way, it really didn't matter if there was a plus or a minus there. I still do that. And in fact, I'm going to say this in a way that I did say in the video, but it's the way I'll probably say it in class. This is a very powerful thing because this tells you that if you're evaluating a limit, you can do it term by term. So an important takeaway is that you can evaluate limits term by term. Now I'm clicking off what I was writing, and you can see that my words are there. So this is an important takeaway, is that you can evaluate limits term by term. You might not realize it, but we're going really fast right now, because what this means is that, gee, I've expanded the way I can evaluate limits really a whole bunch. Okay. Okay, so let's I guess that's good. I've got 2 more that I'm going to do here. So I'm erasing all of that. And this time I'm going to say, what is the limit x tends to c? And this is f of x times g of x. Now, the thing that we learned in the video and that I covered is that the sum of the limits is the limit of the sum, but also the limit of the product of two functions is the product of the limit. And that does assume that both limits exist. So this is the limit x tends to c of f of x. I also did an epsilon delta proof of that, I think, times the limit x tends to c of g of x. Okay, so from the problem, I know that this part is 2, and this part is 3 over 4. And then I, of course, multiply these fractions, and I get 3 over 2 as my final answer. I'm going to pause for a count of 5 Mississippis in case people have questions they want to ask on this. And again, when we're in the classroom, and I really pray every night that we will be in the classroom. When we're in the classroom, you'll just raise your hand when you have questions. I mean, maybe sometimes I'll ask for questions, but I really expect you guys to strive to be active students, and just your questions, I will appreciate them. So anyway, this is 3 over 2 is the answer. I'm counting to 5 now in my head. Okay, and we'll do one more. And I'm going to try, let's see, I guess I am best erasing all this yet again. The last example that I had was this one, the last one in this set of examples anyway, is what happens with a quotient. And by now you're kind of seeing, yeah, this, I sort of see what's going to be happening here. But now I have the quotient of functions. Now, this is not going to work, what I'm doing, if the limit of the denominator is equal to 0, because you can't divide by 0. But that's not this case. So the answer to this then is going to be the limit. The numerator is going to be the limit as x tends to c of f of x. And the denominator is going to be the limit as x tends to c of g of x. But we know what these things are from the givens in the problem. So this is going to be equal to 2, and you could think about it as 2 over 1 if you want, divided by 3 over 4. And if you do the arithmetic, the answer to this problem is 8 over 3. Okay, I'm going to count to 5 Mississippi in case people have questions on this. Okay, no questions, that's good. I'm going to erase this just because we might go back to it again. But now I'm going to share my application screen with you, and we're going to go back to the PowerPoint show. And we did all of these problems, so we've done all of those examples. And Annie, we're looking at PowerPoint now, right?
Yes.
Excellent. Okay, now we're going to do something that's a little bit more subtle. And again, this is a technique I expect you to be able to recognize and use in solving a problem. Now, what we did on everything that we've talked about today only did that, oh, just plug it in. Well, we're going to do more than that, and this is called canceling out a common factor. But now what I'm going to do is I'm going to go through and we'll talk about, I don't know if we'll do all of these, but we'll do a handful of them. Okay, now in number 41, you see the problem is the limit as x goes to 0 of x squared plus 3x over x. And you say, well, Jim said to think about just plug it in and see if that works. But if I just plug it in, I get 0 over 0. And folks, 0 over 0 is not 1. 0 over 0 is called an indeterminate form. It could be anything you want, but it's not 1, okay? And so you have to do some more work on this. So you see, just plug it in did not work for that first problem. Okay, the next problem, number 42, as x goes to 0, if you plug it in and you say, well, Jim said to think about that, maybe only for a nanosecond. Well, I do, but I get 0 over 0. That's an indeterminate form. It's not 1. And so, G, you have to do something else. You have to do the same thing on problem number 43. You have to do something else, because if I plug -1 in there, I get 0 over 0. Now, maybe you're sensing a trend. And in this class, it's probably going to be a rare situation when you can just plug it in on a test or a quiz or, you know, something like that. Because these are the very legitimate, you know, kinds of problems that that we have, and these come up very naturally when we're taking derivatives and so on and so forth. So this is going to be more the norm, but sometimes, and not to shake it up and not to trick anybody or anything else, but I do want students to say, oh, I think about just plug it in. Sometimes on a test or a quiz, I will have something where you can just plug it in, and that's pretty quick. So you do want to think about just plugging it in for a nanosecond. I also will tell you that nature is sometimes kind, and many physical phenomenon are continuous. So there will be applications where you can just plug it in, but also there will be physical applications like this. So let me just say that all of these problems, 41 through 46, is all of these are 0 over 0 when you just plug it in. So none of that works. So this is called canceling out a common factor. Okay, all right, so I'm just going to pick, some of these. I'm going to do number 41. I'm going to write it down. This is x squared plus 3x all over x. That's the limit as x goes to 0. Okay, so I'm going to stop sharing here. And I will go to the whiteboard, which should be blank. Okay, and Annie, I'm going to have a new protocol. If I'm talking about something that you're not seeing, you shout out. Otherwise, I'm just going to assume that you're paying attention and it's all good. Okay. All right. So here, this problem was the limit as x goes to 0 of, it was x squared plus 3x all over x. And then I suggested that you just plug it in to try that anyway. But you say, oh, damn, this is one of those problems where it's 0 over 0. So I have to do something else. Well, we're going to be using the fact, and this was an important fact that I talked about in the videos and in class, that the limit does not depend on what happens at 0. It only depends on what happens near 0. And so what happens is that even though this denominator is 0, when we're evaluating limits, and strictly when we're talking about limits, continuity is another question. But when we're just evaluating limits, you never really get to 0, just like we never really got to the end of that table with a hypothetical frog. And so x is a number close to 0. So that means I can factor the numerator and the denominator. And this is factoring the numerator. And this is, well, there's the denominator. But you see, x never gets to 0, just like the hypothetical frog never got to the edge of the table. So x is a number. It could be 1/2, it could be 1/4, it could be 1 over 1 billion, but it's a number. So I can cancel this with this. So this is the same thing as the limit as x goes to 0 of, now this is x plus 3. And now can I plug it in? And the answer, yes, I can plug it in. So this is 3. But I couldn't just plug it in. What I had to do was factor and cancel out the common factor. So this technique is called canceling a common factor. I'm going to pause for a count of 5 Mississippi in case someone wants to ask questions about something that I did here. Okay, and it is good when there's no questions. It's also good when there's questions. I do want to answer your question. Okay, now I think I need to go back to pick out another one. We're going to do 3 of these, I guess. So I'm going to go back to my application screen, back to Blackboard, or not Blackboard, but whatever this is called. Now 42 is just like that one. And 43, you can do yourself. You get 0 over 0 here. You're going to factor the top into x plus 1 times x minus 1. We're not going to do that, but we will do 44. So I'm writing 44 down here. Okay, so I'm going to stop sharing here. And let's see, and I'm going to do, I'm also going to do problem number 46 while we're on the whiteboard. So, okay, and here we're tending to -2. Okay, so we're going to, I'm stopping sharing here, and I'm going to the whiteboard. So we're here. Okay, and Annie, I'm not asking you, I'm just going to be going and pretending that people can see this. And I'm going to change the color because I am tired of that blue. So I'm going to go try black. Okay, so in this one, we were faced with the problem. This is the one I'm doing. This is the limit as x tends to -2. And actually, this is x tending to -2, so it's like that. And then the numerator is 3x squared plus 5x minus 2. And the denominator is x plus 2. Now, again, if you encounter this problem just along the way, you say, oh, well, I will think just for a nanosecond to see if I can just plug it in. But if you do, you're going to get 0 over 0 again. And so, and you expect that to happen a lot, but sometimes I will give you a problem where you can just plug it in. So now what we're going to do is then try to cancel a common factor. Okay, now the numerator is x plus 2 times 3x, and it's going to be -1. But the denominator is x plus 2. Okay, now just like the hypothetical frog never got to the end of the table, when we're doing the limits, we never really get to -2. We don't care what happens, just for the limit. Continuity is a different issue. But just for the limit, we don't care what happens at -2, but we care desperately what happens near -2. Okay, so since it can't be -2, x plus 2 for any value of x is a number, and it's the same number as x plus 2. So those things will cancel out. And then I will have that this is the limit x tending to -2. And this is 3x minus 1. By the way, there's an important point maybe that I should emphasize here, is that let's see, how do I want to say this? This limit sign is there until I've done it, until I've taken the limit. So you don't drop the limit sign here yet. This is still the limit as, I canceled out a common factor, but the limit sign is still here, is the limit as x tends to -2 of 3x minus 1. But now what I'm going to say is, oh, but now after I've canceled out that common factor, I can just plug it in. And so the answer to this is -7. Okay, I'm going to count to 5 to see if anybody's got any questions on this, and we'll see. Okay, and yes, you do have to factor, okay, because that's one of the prerequisite skills. And to get this problem right, you have to say, well, the correct answer is -7. So to get full credit, you have to have -7. Okay, so I will erase this one and I will go to the last example that I'm going to do in this suite. And this is this problem. I'm staying black. This is the limit as x tends to, let's see, it is -1. And the numerator is x cubed plus 1 all over x plus 1. Okay, and again, I have advised you, and I think it's really true, to think about perhaps only for a nanosecond, but see, hey, can I just plug it in? And the answer is no, I can't just plug it in. So I have to do something else. And so we'll be doing something else. And the something else is, again, going to be, well, actually, there's two something else's you could do. And in fact, maybe I'll make note of that. Now I am typing something that you can't see till I'm finished typing it. Okay, so so I will say since 0 over 0, we have, in this case, it's not always true, but in this case, we have two options, actually. And one is we can do polynomial long division, or we can factor. Now you do have and cancel common factor. Okay, so I'm going off that so you'll see the words that I was typing. Now, maybe you remember this factoring identity, maybe you don't. I think I actually talked about this a little bit during the review, but this is what is true. So I'm just going to write it over here. So a cubed plus b cubed is equal to, you learned this in your algebra class, a plus b times, and this is going to be a squared minus ab plus b squared. And you can check and see that that is true, but that's just some knowledge. You might say, well, I don't have that up here. Yes, you do, because 1 is the same thing as 1 cubed. So you see my top is the role of a is being played by x, the role of b is being played by the cube, and then down here I have x plus 1. So I'm in using that factoring identity, and we are doing this. And so this is going to be x plus 1 times x squared minus a times b here is just x, and then it is plus 1, and it is all over x plus 1. So I cancel out the common factor, which was the whole point, and now I have that this is the limit as x tends to -1 of x squared minus x plus 1. Now I'm going to plug, now again, I'm going to check and I say, oh, can I just plug it in? And the answer is yes, I can just plug it in. And so if I plug in -1 here, I get -1 whole squared is 1. This is a minus 1. You do have to be careful with your signs. And this is +1. So the answer to this is 3. So I'm going to count to 5 Mississippi in case people have questions on this, and we'll see. Okay, excellent. I'm going to erase all this in case we have to go back to that again, and I'm going to share yet again your applications screen. And there we are with the application screen, and I'm back to the PowerPoint. And we did a bunch of those. You should do some other ones. But now we're moving on to a different thing. And this is another technique that I did introduce in the video. I did several examples in the video, you know, the one from 3 o'clock this morning. And that is called, I'm going to call it, there's a whole bunch of different things you could call it, and I'm not going to ever ask you, what do you call this? But you could call this rationalizing either the numerator or denominator, or you could call it creating a common factor. So I'm going to do this problem 56 as an example of that. So this is the limit as x goes to 0 of square root of 2 plus x minus the square root of 2 all over x. And I'm going to have to write that again on the chalkboard, so I'm stopping sharing this. I'm going back to Blackboard, or whatever this is, Collaborate Ultra, and I'm sharing a whiteboard now. And I will do this. So the problem I've asked you to do is this one. And again, there are many more examples of this that I discuss in the video. So this is x goes to 0. This is the square root of 2 plus x minus the square root of 2. And this is all over x. Now, you know, you've heard me say that what I expect you to do is I expect you to always think, even if it's only for a nanosecond, and a nanosecond's not very long, can I just plug it in? But if you do, you say, well, I get 0 in the denominator and I get 0 in the numerator, so this is 0 over 0 again. So just plugging it in doesn't work. But now, and this is a new technique for us in this class, I guess, but it is a actually we reviewed this during the algebra review. But you see, you don't change, there are two very sophisticated techniques. They sound simple, but sometimes they're very sophisticated in practice. You can add 0 without changing the value of something. And you can multiply by 1 without changing the value of something. Now, sometimes you have to add 0 in a very clever way. And sometimes you have to add multiply by 1 in a very clever way. But we're capable of doing that, and we are going to do it here. But you see, just plugging it in doesn't work. And you might say, oh, yes, but I will factor this. Well, this is not easy to factor either. There's no factoring that happens here. So you can't say, oh, I'm going to cancel out a common technique. So this is a third powerful technique to modify things so I can do it. So what I'm going to do is I'm going to multiply top and bottom by, I'm going to multiply by 1, but it's 1 in a clever way. And sometimes a student will say, how did you know to do that? And my answer to that is, it is tradecraft. Someone taught me how to do it, and I am teaching you how to do it. So it's just something you say, oh yeah, I know how to do that. So I'm multiplying by 1 in a clever way. But the way I'm doing a clever way is by multiplying by what is called sometimes the conjugate of the numerator. So this is going to be the square root of 2 plus x minus the square root of 2. And so the conjugate of that is the square root of 2 plus x plus the square root of 2. So you see we've multiplied by 1, so we haven't changed anything. But now we're going to do the calculation inside here. And this requires you, and this is what really motivated the thing, there's a factoring formula that we reviewed whenever we were doing our algebra review, and that is that a squared minus b squared is equal to a plus b times a minus b. Okay, so you see I've got the role of a is being played by the square root of 2 plus x, and the role of b is being played by the square root of 2. So when I multiply this, the middle term drops out. You see I'm over here, I have a minus b times a plus b. So I'm just going to get a squared, and again, this is still the limit as x goes to 0. And now a squared in this problem is the square root of 2 plus x whole squared, and that is 2 plus x. And then what we have here is, so that is a squared, and then this is minus, and b squared is just 2. And then this is all over, and this is x times the square root of 2 plus x let's see, that's an hour. So that's 2 plus x. I need to make that square root longer there, like that, plus 2. Now, everybody, please notice I'm not dropping my limit sign. One thing I encourage students to do is be precise when they're doing mathematics. And a lot of students, they just would throw down an answer and all kinds of things like that. Please don't do that. You haven't taken the limit until you've taken the limit. So what we have now is, now I'm doing some arithmetic, and so here the 2's cancel out, but I have x over x. I screwed that up. That's the square root there. And again, the parentheses matter. So that is the square root of 2. Okay, now remember that the limit has nothing to do with what happens at 0. The hypothetical frog never got to the end of the table. But so we're getting numbers that are close to 0, but x over x isn't, you don't have 0. I cancel that common factor. And so now what I have is that this is the limit. X goes to 0. Now this is 1 over the square root of 2 plus x plus the square root of 2. And now you see we can just plug it in. When we plug x to be 0 in, I get, and this is the answer, I've run out of room to put it, so I'm just drawing a line there. This is like on a different board or something. So the answer is 1 over 2 times the square root of 2. Now, some of your, in fact, I will tell you a story about me. I was educated by nuns when I was young, and the nuns taught me that in fact, I will tell you what I thought. I don't know if they actually taught me this or not, but I thought I would go to hell if I didn't multiply top and bottom by the square root of 2. Well, it's important you know how to do that, and it's important you understand that, but this is a fine answer to the problem. This is the exact answer to the problem, and this is something I would count right. Okay, so that's that one, and that's I'm going to count to 5 Mississippi, just to see if students have any questions. Okay, very good. So I'm going to erase this. Okay, and I'm going to share my applications screen, but I'm doing something else now. Let's see, so it is 2585. So we go till 10:55 for you to get your money's worth. Or so let's see, because it's you are paying for 500 minutes of quality in instruction. Or wait, let's see, it's 5 times 50 is 250, and so if we divide 250 by 3, we get 83. We started at 9:30. 10:30 is 60, and so we go to oops, I guess that's 45, isn't it? Because well, wait, that'll be I'm doing some arithmetic now. I'm actually going back to the whiteboard. Okay, so so what I want to do is I do want you to get your money's worth. So 9:30 to 10:30 is 60. So we need 25 more minutes, and that means we go till 10:55, and that gets you above 83. Okay, so that's 85. So I'm giving you a little bit extra, but that's okay. All right, so we're going to be working for about 12 more minutes. Okay, and that's enough time to continue. So now I'm going back and sharing my applications screen. And we'll go to PowerPoint. And now we're going to talk about a theorem that I did not talk about in the video. So this is new stuff. You're getting this in class today. I do expect you to, understand this, but this is a new thing. And this is called the Squeeze Theorem. Now, we might not get to it, but we are going to be using the Squeeze Theorem in a something very, very soon. So this is the statement of the Squeeze Theorem, and it is a graphical representation of the Squeeze Theorem. And this is an important theorem. There are problems that you can't do unless you have this in your toolkit. So let's talk about what the Squeeze Theorem says. Now, there are 3 functions involved in this Squeeze Theorem. There's a function that is less than f of x, and we're calling that h in this statement. And there is a function that is bigger than f of x in this statement of the theorem. But it's not always true, but it is true. And the way I could say this is, I don't know if this is, we'll see if this works. Yeah, I think that worked. Okay, so this says for all x in an open interval containing c, except possibly for c itself. Now that except possibly for c itself, this theorem is about limits, and that means we really don't care at all what happens at c. We care very passionately about what happens near c. That's a subtle point. I know I keep saying it, but it is an important point. Okay, so you see near C. Now here is C, and near C, I could have a, let's see. I don't want to do it that way. Let me try this. That's not going to work. This might work. Okay, so near C, within a neighborhood of C, this is so tedious. Okay, so we go there. Okay, so around C, a neighborhood of C, and again, if you study the epsilon delta proofs like I asked you to, what is happening is this is maybe C minus delta and this is C plus delta, but is near there, this inequality holds. The inequality that I talked about, that H is less than or equal to f of x is less than or equal to C. And this is still part of the if part of the theorem. So the if part of the theorem, and so this is part of the if part of the theorem. The limit as x tends to c of h of x is equal to L, and that's the same thing as the limit of g of x is equal to L. Now what that means is, as you're getting, and I hope you can see me wiggling your cursor, people have told me you can. So as you get closer and closer, you see the function f that is between H and G is being squeezed tighter and tighter as you're getting closer and closer to C. So that's the if part. So if you have these inequalities existing near the point C, but we don't care about C itself, and if both H and G go to the same place, they go to the same limit, L, then there's two conclusions that are being listed here. And there really are two conclusions. One is that the limit as x tends to c of f of x exists. And you know from your videos that limits don't always exist. And so the limit as x tends to c of f of x exists. And moreover, you know that the limit as x tends to c of f of x is forced to be L. Now, I sometimes do a little demonstration in class with some students. You're not getting the benefit of that, but there's the statement of the theorem, and this is an important theorem. So I'm going to be pausing now for a short time, maybe a count. Well, actually, I'm going to pause maybe for a beat of 10 Mississippis because this is important and we're going to be using it very soon in case people have questions on understanding this theorem. Now, I haven't proved the theorem yet. I may prove the theorem or I may not. I'm watching the time carefully and I work very hard to use my time productively. So anyway, I'm counting to 10 now. So if you have questions, please ask them.
Is it okay if I just quickly write this down?
Of course. In
Okay,
fact, I
I'll
would
let you know when
encourage
I'm done
students.
writing.
Okay, I will do that. And in fact, I'm going to be counting while you're doing that. I'm counting silently in my head. And I am going to be talking a little bit whilst that may have been Cecilia, I'm not really sure, but whoever is writing this down until they tell me that they're good, I'm just going to talk a little bit more. And so the way we'll prove this is using epsilon deltas. And I am going to show you that proof. I don't know if I'll end up showing you the proof today, but I might. And then I actually was prepared to use this to solve, to prove a theorem, and maybe we'll do a little bit of a look ahead and so on with that. And again, it's possible to do well in this course and not be good at epsilon delta things, but I really think an A student would be good at epsilon delta proofs as well. if any of you end up going to the GSGs when we have them and things like that, Linda probably would appreciate being congratulated. That actually was kind of a big deal that her team won the regional championship, the math club. It speaks well of her. So anyway. Also, you're coming up on a weekend, and for whatever it's worth, I do math every day, and serious students often do math every day. It is good for them. So if you're behind on some videos and stuff like that, don't get worried, but just get caught up. So how are we doing on this?
Fine.
Great. Okay. And thank you for asking. That was, I mean, that was good. And actually, some of the things, in fact, pretty much everything I talk about is important. This is the proof, and we have 3 minutes left in the period. I'm not going to do this proof. In fact, I may do this proof in a video. This is an epsilon delta proof, but I'm going to race ahead because I've got I have examples and everything else. Okay, this is my cockpit commentary because we got like 3 minutes left in the period, and I'm talking to you, and I'm talking to the class at large, and I'm really talking to you pretending I'm a pilot, but actually I think that's a pretty apt analogy. We took off, and I deliberately did a steep ascent to reaching our cruising altitude. And in fact, I didn't say it here, but we're pretty much at our cruising altitude. Now, that was a steep and rapid ascent because I didn't want to try to teach you all the math that you've learned. We did do reviews in those videos, and that was some pointed reviews, and it was, I think it was good reviews. I never could give enough review, and it's important that you just realize you're going to have to remember things, and so you'll deal with it. But for the most part, we're going to be remembering that in the context. So we've been going very fast through that review, and it was a steep ascent, and you probably felt some G-force and things like that associated with it. But we are at our cruising altitude and speed, and we're very well positioned in this course. 1 week of the course is done, and we've accomplished a lot. Now, some of you are just getting used to this. I wasn't wanting to be doing this online to start with, although I'm very well prepared to do it online. I'd rather be doing it otherwise. But I realize that you guys are juggling it, you're getting used to things and things like that. So you might not be fully caught up. Do not do what that discrete math student did, and I'm not telling you the person's name or anything. I wish that discrete math student has talked to me, because I say, don't drop the course. I mean, I hope it's not going to be online forever. You have an opportunity this weekend to catch up. So my message to you all is, do not quit. And this is something that a famous football coach once said, but only those who stay will be champions. My goal is for all of you to be champions. That's the cockpit commentary. This is my benediction. Now, more than ever, time is precious. Each day must count. Do the math, it will make you strong. And now, more than ever, take care of yourself and each other. Now, I stopped sharing that because I heard someone make a noise here, which may have been a comment. And Harry Patel, I think, and by the way, I'm not identifying, but it was fine asking the question. When will post the LSA 2? I maybe have to post LSA 1, but I will post LSA 2 too. And by the way, I use the weekends to catch up as well. So that's my answer, and that's pretty much the class for the week. It is important for young people to be careful on weekends, so please be careful. Okay, take care.
Thank you very much, Professor. Have a great weekend.
Bye. Have a good
Hey, Professor.